Good day! I am JM.
I am Ernesto.
I am Sarah.
I am Rain.
And we are going to present about our antenna project.
So to begin, the outline for these presentations are the introduction, design, computation, testing and scoring, and then the conclusion. Let's begin with introduction. So what is an antenna? An antenna is a device that is made to efficiently radiate and receive electromagnetic waves. There are two branches of antenna. The transmission radiates electromagnetic energy into space. Then, the reception, which collects electromagnetic energy from space. The television antenna, TV signals are transmitted at frequencies from about 47 to 250 MHz in the very high frequency band, and 470 to 960 MHz in the UHF band or ultra high frequency band. Television antennas can be classified into two, indoor and outdoor. For shorter elements which receive the UHF stations, the most common is a Yagi antenna. So what is a Yagi Uda antenna? It is a directional antenna consisting of a single driven element connected to the transmitter or receiver with a transmission line and additional parasitic elements, which are not connected to the transmitter or receiver. A so-called reflector and one or more directors. Yagi antenna is widely used where gain and directivity are required from an RF antenna design. So for the design of this project, it will be presented by Ernesto.
Hi, in designing Yagi Uda Antenna, there are many factors to be considered. First factor is, what is our target frequency that you want to get? So, as you can see, these are the channels that we want to get, or our certain frequencies that we want to get in our Yagi Uda antenna, which is belong to the ultra high frequencies or the 300 MHz or 3 GHz. That is why we use Yagi Uda antenna, because Yagi Uda antenna is used for ultra high frequencies. So first, what are the parts or the composition of the Yagi Uda antenna? So first we have the reflector. So the reflector is made to be 5% longer than the driven element. So the Yagi antenna will generally only have one reflector. This is behind the main driven element or the dipole. So next is we have the dipole or the driven element. So driven element is the Yagi antenna element to which the power is applied. It's normally a half wave dipole or often a folded dipole. So the dipole is where the balloon or the transmission line is connected. So next is we have that director. So the directors are made to be shorter than the driven element. They may be none. One of more reflection antenna. It is used for sensitivity. So now, as you can see, these are the wave flow in or the radiation pattern is flowing in our Yagi Uda antenna. So first we have the distracted inference. So these are low frequencies. Then after the reflector and the driven element or the dipole will transform our destructive interference to the constructive inference, which will transform these waves into more greater amplitude. That is why we're able to get the ultra high frequencies. So next is these are our frequencies that we want to get. So first we put what is the lowest frequency, which is our lowest frequency in our channels that we want to get, and the highest frequency is 700 MHz. So after that, we want to get our center of frequencies, because it will be the basis for our construction in the Yagi Uda, which will be discussed this computation by one of our classmates. Next is Yagi Uda construction. So we have aluminum rod, aluminum beam, and coaxial cable. So you may be thinking, why we use aluminum? Because aluminum is twice conductive as copper, and then it is 6 times more conductive than steel. So it makes an excellent choice as an antenna material. So the increased electrical efficiency means more of your RF energy will go up and out of the antenna and not be trapped, creating heat energy. So next is we have the balloon. So as what I've said, it is for a transmission line. This one is the one who is connected in the dipole or the driven element. So we have bolts and nuts and holders. So it is for our aluminum rod. Next is computations, which will be discussed by Sarah.
For computations, length measurement, we have the center frequency, The center frequency is equal to the square root of the highest frequency multiplied to the lower frequency. In this project, we used 700 MHz for highest frequency and 450 MHz for lower frequency. The center frequency is equal to 561.2486 MHz. For wavelength, we have the speed of light divided by the frequency. For the speed of light, we have the 3 times 10 raised to 8, and the frequency, we have the center frequency, 561.2486 MHz. And then we have the wavelength of 0.5345 meters. Next, we have the dipole or the driven element. For the length of the dipole, we have 0.5 wavelength. So 0.5 multiplied to the wavelength, which is 0.5345, we have the length of the dipole to be 0.26725 meters. For the reflector is made to be about 5% longer than the driven element. So we have the length of the reflector is equal to the length of the dipole plus the length of the dipole times 5%. So we have, for the length of the reflector, we have 0.2806 meters. Next, for the director. The director is made to be 5% shorter than the driven element. So we have the length of the director is equal to the length of the dipole minus the length of the dipole times 5%. The length of the director 1 is equal to 0.2539 meters. Next, for the length of the directors. We have the director 1, 0.2539 meters, director 2, 0.2412 meters, director 3, 0.2291 meters, director 4, 0.2177 meters, director 5, 0.2068 meters, director 6, 0.1965 meters, director 7, we have 0.1866 meters, and director 8, we have 0.1773 meters. Next, for the spacing measurements, we base it to the study of optical design of Yagi Uda Antenna for VHF band application using Magos 2.2 software from the Department of Electrical Electronics Engineering from the University of Agriculture, Makurdi, Nigeria. So for spacing measurements, we have the reflector to the dipole-driven element. We have the range of 0.25 wavelength to 0.35 wavelength. For this, we use the mean, which is 0.25 plus 0.35 divided by 2, which is 0.3. So we use 0.3 wavelength, 0.3 multiplied to the wavelength, which is 0.5345. We have the spacing between the reflector to the dipole or driven element to be 0.1604 meters. Next, we have the spacing to the driven dipole element to the directors. We have 0.125 wavelength, so we have 0.125 multiplied to the wavelength, which is 0.5345, and it is equal to 0.0668 meters. Next, we have the spacing between the directors. The range is 0.15 wavelength to 0.25 wavelength. Again, we use the mean, which is 0.15 plus 0.25 divided by 2, we have 0.2. We use 0.2 wavelength, the formula, then we have 0.2 multiplied to 0.5345, we have the spacing between the directors to be 0.1069 meters.
Hi, I am Rain, and I will present the testing and scoring. Because Yagi Uda is a directional antenna, the height and the direction of the antenna where it is facing affects the clarity of the reception. For this outline, we have rated the receptions whether if it's clear, static, moderate, or no channel based on the two trials that we have conducted. For trial 1, we tested the Yagi Uda at 3.02 meters height from ground, in which we have captured the reception for each channel as shown in the table. With the same height of 3.02 meters from SEM building 4th floor, we have conducted the second trial. The result is shown here.
For conclusion, the Yagi Uda concept of antenna was chosen by the proponents due to its capability of having high gain in increasing signal strength. The point of having high gain is to attain a better reception and a more accurate way of targeting radio signals in long-range wireless networks. Yagi Uda antenna has two basic elements, which are the active and the parasitic element. The active element are aluminum rod, which is called a dipole, that act as a feeding point of the signal and is connected to a transformer that converts unbalanced to balanced signal known as a balan. On the other hand, a parasitic element are array of aluminum rod that act as guide in increasing radiation indirectly. The parasitic element is composed of a reflector and director. A reflector is located at the back of the feed point where is used to bounce back the radiation into the dipole, while the director is to guide the radiation into the direction of the dipole. The gain in Yagi Uda is determined by several factors, which are the number of directors, element spacings, and the length of elements. However, the most critical factor would be the number of directors. Typically, a reflector produces 4 to 5 decibel of gain itself. This is because the radiation is doubled since it bounces back into the dipole. Then, each directors added provides a roughly 1 decibel of gain. The formula in calculating the gain of Yagi Uda is defined by G is equals to 1.66 multiplied by N, where the N is the added element. Therefore, the gain for this Yagi Uda antenna results to 14.94 decibels.
울고 싶지 않아 울고 싶지 않아